my name is Peter de Bock, and I'm a Program Director at ARPA-E. We prepared this webinar on exploring transformational technologies for cooling data centers more efficiently. And this is a topic we've been interested in for some time. The purpose of this webinar is to convey how we think about this space and highlight a few areas that we think could be ARPA-E programs going forward. What we'd like to get out of this is more engagement with the community. We'd like to hear your ideas. We encourage you to send us white papers, and if there are funding opportunities going forward, we encourage you to submit your applications.
First, I'd like to recognize Rakesh, Vivian, and Carlos, whose contributions helped to make this presentation. At ARPA-E, we focus on stimulating transformational technologies that reduce energy consumption, increase efficiency, and deliver impact that matters. This makes us look at potential areas where we see that significant energy is used and where technology can make a difference. One of these areas we are exploring is data centers. Data centers are buildings that house rows and rows of servers that are used every day to host our digital applications. The importance and growth of the sector has been tremendous. In just a decade, the internet traffic grew 500%, and the number of data centers has grown significantly. Total energy usage of data centers in the US is about 75 billion terawatt hours. Now, not all data centers are created equally. Data center efficiency is often expressed in power usage effectiveness, or PUE. This is defined as the total energy consumption divided by the IT load. A PUE of 1 would be ideal. On the chart below, you can see the PUE for a variety of classes of data centers. The very large hyperscale data centers are actually quite efficient, and this is often achieved by siting them in favorable climates that are cool or dry and use water evaporation in the economizers or cooling towers. The remaining 5 categories, from closets to high-end data center types, are significantly less efficient and use about 33 to 40% of their energy for cooling. In these categories, which cover more than 50% of all data centers, have to do this because they are often closer to the customer. They are not in a favorable climate and therefore need air conditioning systems to operate within temperature specifications. As we look forward to the next decade, 2020 to 2030, we expect the number of data centers to grow. In addition, we expect the way people interact with their data to change. There's potential for more mission-critical applications. And this is where large data sets inform machines and systems live. This can be in healthcare, industry, engineering design, transport operations, and all of these require fast, low latency communication with data. This is also referred to as edge or aggregated edge computing. And these systems often do not have a choice of being located in a favorable climate and will therefore have higher energy usage. If you think about it, the computer chips typically run at 60 to 90 degrees Celsius. And since ambient temperatures are much lower than that, heat should flow naturally from hot to cold. This is the second law of thermodynamics. So why do we need to use energy for air conditioning in the first place? Why do we need air conditioning, which is a heat pump, to cool these data centers? Can we reimagine cooling for these 5 categories of data centers so that they no longer or barely require air conditioning at all? A baseline cooling system for a server is sketched below. Cool air goes into the server, heat from the processors heat the air, and as much heat as possible is rejected with the economizer, and the remainder is cooled with the air conditioning loop. And the refrigerant that's in the air conditioning system is cooled with outside air. What we would be interested in is to hear your ideas on transformational technology concepts that reduce the thermal management energy needs of small, medium, and large-sized data centers by 80 to 90%. Basically anything but hyperscale. And this could potentially eliminate air conditioning or make it very high lift, so its coefficient of performance and efficiency is much higher. If you do the math, such an improvement in thermal management would result in a PUE drop from 1.6 to 1.1 for these smaller data centers. And as a bonus, we would love to find innovative ways to do this with much less water usage, which we know will be very hard, but it's something we can also explore. If you look at technology concepts, we want them to have the potential to commercially scale to a high reliability. And in addition, we'd like to see paths of cost that can lead to competitive cost and operational advantages for the data centers going forward. To give you a bit of direction of the word location independence above, we'd like just people to consider a climate that is pretty challenging, perhaps Washington, D.C. in summer, which can be pretty hot and humid. In order to achieve these pretty challenging goals, we envision the thermal chain from chip all the way to ambient to be reimagined completely. And on this slide, we are presenting a few creative ideas for teams to consider, but we definitely do not want to limit you by these concepts. We want to hear any good idea that can help us achieve a leap in energy efficiency for this space. First, we have depicted here what we call bio-inspired cooling. We cool electronics by blowing a lot of air over them. The air comes in cold and leaves hot. Nature is cooled in a very different way. Leaves, trees, and plants can sit in the full sun all day because they slowly transpire a small amount of water through little holes. Can we cool electronics in a similar way? We'd like to hear from diverse teams, perhaps biologists who normally don't work on data centers, but can bring some new creative insights to this mission. We'd like to see what new manufacturing modalities, such as additive manufacturing, can also bring to this space. We can additively manufacture aluminum, copper, and even ceramics. What can new geometries envisioned now be able to be created to use these modalities? Can they help us get closer to the heat source, the chip, the junction, and how can we use these new technologies to create an even lower thermal resistance path? The third area to consider is new concepts regarding HVAC and dehumidification. When water goes from liquid to vapor, we can expect that it takes energy. When we try to go from vapor back to liquid, there are potentially mechanisms that can do that without costing so much energy. And it would be even better if the fluid can be recaptured or harvested. One of these concepts is shown here, is developed by David Claridge at Texas A&M and Dr. Liu at PNNL. This concept actually removes the humidity from the air using a membrane and is able to recapture it. These are the kind of ideas we'd like to see explored for a data center. And last but not least, we are interested in transformational system concepts. Racks, servers, and data centers have all looked the same for several years. Can we reimagine the designs to be more optimal? Can we co-design from chip all to HVAC to ambient in a single optimization study? Perhaps these are additional benefits that can be. Perhaps there are additional benefits that can be generated to make a data center more efficient. And as said before, these are concept ideas, and we do not want to limit your imagination. We want to encourage you to engage with us and send us white papers. And if there are funding opportunities going forward, we look forward to see your applications.